Depending on your goals, you can approach the task of modeling airplane physics in different degrees of realism. More often than not, some sort of an arcade controller will suit your game better and feel cooler than a true-to-life simulation. Yet in this video I am going to show you how to make more or less realistic model. I have two reasons for that. The first one is, of course, you can make something that flies kind of like a real plane, how cool is that? But it can also be handy for someone not interested in making hardcore flight sim. Recently I played Ace Combat 7. It is an arcade game about fighter jets that is not concerned with adhering to the laws of physics. But it still, in some form, includes effects like stalling or dependence of maneuverability on airspeed. For me, it makes the game kind of charming. I think getting a feel of a realistic simulation can give you good ideas even for an unrealistic game. So the question is, how do airplanes fly and how can you model it in a game? Let's consider the forces acting on an aircraft, which are important for our problem. There is of course force of gravity or weight pulling the plane down. For the powered aircraft, there is also thrust, which pulls it forward. It can be created by various methods of propulsion like propellers or jet engines. In our simulation, we will just apply a force in the direction of the airplane nose. And then there are aerodynamic forces, which result from the interaction of the plane with the air as it moves through it. Aerodynamic forces are usually divided in two components, lift and drag. Drag is parallel to the flow direction, while lift is perpendicular. Instead of looking at the plane as a whole, let's break it down into several parts and consider them separately. By doing so, we neglect the changes of airflow around an element created by the other ones. For example, the disturbance of air behind the wing or downwash can alter the performance of the tail. There are ways to account for that, but in this video we will stick to individual components for simplicity. How can we calculate aerodynamic forces acting on a single plane's part, like the wing? We can't solve Navier-Stokes equations describing the underlying physics in real time, so we need to simplify. For this we can use much simpler equations. They describe the forces and torque acting on a wing in terms of airflow speed, air density, wing area and numerical coefficients. But why do these formulas look like they do? Let's figure it out. Consider a flat plate submerged into the flow of air with speed v and density ρ, directed perpendicular to its surface. I know it doesn't look like a normal situation for a wing, but bear with me here. We want to know how much force the air applies to the plate. According to Newton's second law, the force equals the time derivative of the body's impulse. Or to put it in a different way, the change in impulse divided by the time during which the change happened. Let's make an estimate of the impulse change delta p during some small time delta t. Suppose that impulse transferred to a plate is proportional to the combined impulse of the air particles which can reach the plate during this time. The value of the numerical coefficient depends on the details of the particles' interaction with the plate and themselves. I've also multiplied the right-hand side by half to follow the convention. The impulse equals mass times velocity. The combined mass of the particles is volume times density of the air. During the time delta t, particle can cover distance v delta t. The volume containing the particles which will reach the plate is then equals the distance times area of the plate. When we substitute the result into the Newton's law, the delta t's will cancel out and we'll get something very similar to the formulas we have seen earlier. Coefficients of lift, drag and torque are not constants and depend on many factors. Three most important ones are angle of attack, Reynolds number and Mach number. The angle of attack is an angle between the airflow and the wing's direction. The Reynolds number depends on the density, speed and viscosity of the fluid and the size of the wing. It describes how turbulent the air is. The Mach number is the ratio of the air velocity to the local speed of sound. It is very important for the flight at the speed near or over the sound barrier. In this video we'll consider only flight at low Reynolds numbers with subsonic speeds, so coefficients will only depend on angle of attack. I may come back to Reynolds and Mach numbers in a future video. Let's look at typical lift and drag coefficients dependencies on angle of attack. At low alpha, drag is small and lift is proportional to alpha. How the wing performs in low angle of attack range depends on its cross-section. There are special shapes designed to maximize lift while minimizing drag, called airfoils. At larger angles of attack, lift becomes larger, but so does drag. At some critical angle, usually around 15 degrees, so-called stall or flow separation happens. The way the air flows around the wing changes and the amount of lift decreases. The effectiveness of control surfaces also diminishes. In this mode, the wing performs more or less like a flat plate. Aerodynamic coefficients are usually computed in detailed simulations or measured in wind tunnels. You can compose an aircraft for your game by digging up data for various parts obtained in these ways. But this is not a flexible solution, because you are limited to the stuff you found. There is also a problem of control surfaces. So far we have looked at the coefficients of the wings with fixed shape, but they often have a moving part that can change its parameters on the fly. With those in mind, you would have to either find a detailed data table for the various alphas and control surface positions, or come up with it on your own. This is quite difficult. But while researching for this video, I stumbled upon an article concerned with modeling toy planes in real time. It describes analytical equations for calculating aerodynamic coefficients for an airfoil in the full range of angle of attack. The model also considers the effect of a flap, which allows for easy control surfaces implementation. The aerodynamic element in this model is described by few understandable and easy to tweak parameters. Lift slope describes how much lift surface generates at low angles of attack. Skin friction coefficient determines how much friction the surface creates with the air. Zero lift AOA is an angle of attack at which surface generates zero lift. Stall angle is a critical angle at which stall happens. Chord is the length of mean chord in meters. Flap fraction is the size of control surface relative to the mean chord. Aspect ratio is the ratio of the surface area to the square of mean chord. With lift, drag and torque formulas and aerodynamic coefficients, we can calculate the forces acting on an element. Now let's pull them all together. We need to know the flow velocity around each element. It consists of aircraft center of mass velocity, velocity of the element due to rotation, and additional velocity due to wind, propeller wash or other things. Then we need to transform the result into the coordinates relative to the element. We'll discard the component of the velocity which goes along the surface perpendicular to the chord. It only causes skin friction and isn't involved in normal lift and drag creation. From the resulting velocity we can get dynamic pressure and angle of attack, from which we can compute the coefficients and eventually forces and torque. Then we need to apply them somewhere. The point of aerodynamic forces application or aerodynamic center is usually placed around the quarter point of the chord. So to transfer these forces to the aircraft, we need to apply them directly to it and also add corresponding torque due to their displacement relative to the center of mass. Then we need to add torque acting on the element itself. I've implemented this thing using rigid body to control the motion. I calculate aerodynamic forces and apply them to the body using add force in fixed update. But this means that forces can change only once every physics update. Since the values of the forces are dependent on the velocity and angular velocity of the body, having large fixed delta time can lead to some nasty effects. In this example, I have lowered the physics frame rate to 30 FPS. With forces updating once in a frame, the physics can sort of overshoot and will get this jitter. With more nimble aircrafts, it can get bad even for 60 FPS. You can solve it by making fixed delta time smaller, but it is not always desirable. So let's solve this problem in a cheaper way. The algorithm is as follows. We calculate the forces according to the current velocity and angular velocity values. Predict the velocity and angular velocity in a half of time step according to the forces that we've got in the step 1. Calculate the forces according to predicted velocities. Apply an average of the initial and predicted forces to the body. By this, we are effectively creating a substep specifically for aircraft physics. Since it's quite cheap, it won't make a toll on performance, unlike increasing the general physics frame rate. Source code is on my GitHub, as well as some examples and tips on how to make a plane.